Guess we can get started. So today I'm working from home and I left my, what happened there? Why is it saying this is no longer active? Let's try this again. Okay, technical difficulties. Okay, so I left my Surface at work and I'm at home, so I have this other drawing tool. It's actually a lot more accurate, but it is smaller and I'm sorry for that. So today, theoretically, supposed to be moving into SN1 chemistry, which if we're looking at the schedule is lecture number something. Lecture number 20. So at this point, we should be all caught up and moving on to this. There's a lot of stuff in lecture number 16. It's a very long lecture. We covered 17 through 19 with the carbonyl stuff. So I'm open to discussing any questions first of all anyone has about SN1 chemistry. And if not, we can cover stuff from the stuff we just talked about last class. Remote classes. Why do I sound sad? You know, as Madeline pointed out, I think we got about 35 of you guys in here, so we're about 10% class attendance. So for online Zoom classes, attendance ranges between about 5 and 25% generally, if they're asynchronous like this. That's what all the research tells us. So normally we're at the top end of that spectrum. Today we're near the bottom end of that spectrum, and that makes me sad. I think we're all just tired, right? So there's a lot of lecture 16 is so long because the stuff is so hard. So I go over the mechanisms in detail. But if anyone wants one particular one to go over again and I can walk through it, but I'm probably going to sound like I do on the videos because I think I'm still thinking about these things the same way. But the whole point of this is that it's interactive, right? So you can ask questions. I also hate November. November is a shitty month. No one likes it. Okay, so I covered the hydroboration, deboration last class. I'm going to try and do the hardest mechanism, I think, in the entire class, which is in there. So let's talk about ozonolysis. Oh, I'm very happy for you, Joshua. Do I have any tips and tricks that'll help do these more efficiently? No, what I recommend you do, though, is you generate like a simple, almost all the cases we've talked about, and for this course, almost all of them, they're not, we're really defining using the reagent. The reagent really determines the reactivity. So, you know, the substrate needs to have a specific functional group. That's important. But other than that, no, Melitza, you're asking the questions for the class. I could definitely go over an oxymercuration. That fits directly with what we were just talking about, Hannah. Yeah, I'll do that. So what I recommend you do is build basically a cheat sheet. Like, it's fine. It's not a cheat sheet. This is an open book exam. You can go look this information up. But it's better, I think, if you have a list of the reagents you need and what the transformations they do, and then you have sort of a raw version of the mechanism sketched out. Now, there are always details. Every single one of these is different. As somebody pointed out, how can you memorize this when everything's different? It is, but the patterns are the same. And so I recommend you do that. Strongly recommend you do that. So if I'm, well, you know what? Let's do an oxymercuration demarcation first. So I'm just going to make this guy different. So the idea behind an oxymercuration is that you're using, it's a Markovnikov addition. But we're not using strong acid. So when you do a Markovnikov addition of water, you need something like sulfuric acid in water. And there are all sorts of reasons you do not want to put your molecule into sulfuric acid. Maybe you have one of those acetals that we made last couple classes ago in there. The sulfuric acid will break that down into the ketone. But generally, you know, strong acid just destroys stuff because it's a strong acid. So if your molecule is complicated, I can say with a lot of confidence, I have never run a Markovnikov addition of water my entire life. I am probably never going to run a Markovnikov addition of water. If I need to add water Markovnikov, I'm going to do this. The reason is because it's much more gentle and it's much more selective. Now, it does involve mercury, and mercury is horribly toxic and kills people. But this isn't the bad type of mercury. Organomercuries are really nasty. And we're going to make an organomercury, but you're going to break it too. So mechanistically, what we need to realize here, it's the same thing as everything else. What is the most reactive species? And I've drawn, I actually haven't explained what OAC is, have I? Which is fair. Sorry, I just sketched it like that automatically. So we have mercury, Hg, bound to two acetate groups. Acetate groups are the acetic acid conjugate base. Those of you who are taking the inorganic chemistry are seeing a lot of acetates, I'm sure. Organic chemists, inorganic chemistry. Inorganic chemists love acetates. So if we're thinking about this, let's look at any one of those mercury-oxygen bonds. Which way is that polarized? First of all, what is mercury? Is mercury a metal or an organic molecule or kind of in the middle? Great. Okay, thanks, Hannah. It's a metal. Yeah, mercury is a metal. It's pretty heavy metal. I'd accept kind of a metalloid as well. It's a little weird, right? It's this liquid metal. It's an odd ass metal. But if you look at the electronegativity in mercury, whenever you have a metal oxygen bond, yeah, it's covalent, but it's also kind of ionic. It's kind of in that middle ground. So this is essentially our H+ equivalent. It's not hydrogen, it's mercury, but it does the same thing. I don't have any color today. This is a beautiful, beautiful tablet, but it only does black and white. And it has no internet connectivity, and I really do love it because it feels like writing on paper. Except unlike paper, I don't lose everything because I just write on scraps of paper and then I forget which scrap of paper I wrote on, and I misplace a scrap of paper, and next thing you know, like the password to my Bitcoin wallet is missing. That's not a true story. I don't have a Bitcoin wallet. But, you know, something important is missing. And I can never find it, and I just recycle it because I ran on the back of something. So the idea is that if I put all my notes into a single thing, I won't lose anything. So far, that's not working very well. Okay, so we're generating a more stable carbocation. Okay. So Melitza asked a really good question. How do you know a double bond acts like a nucleophile or electrophile if the reagent has a positive or negative and negative partial charge? We have not seen a carbon-carbon double bond act as an electrophile. It can happen. We haven't seen a single example of it. Every single time we've seen a carbon-carbon double bond, it's acted as a nucleophile. We have also not seen a carbon-oxygen double bond act as a nucleophile. We have only seen it act as an electrophile. And that comes down to the electron density of the bond and where the orbitals are and all this stuff. But suffice to say, carbon-carbon double bonds are mostly nucleophilic. You need a stupid strong electrophile to react with them. And carbon-oxygen double bonds are mostly electrophilic. You need a super strong electrophile to react with them to make them nucleophilic. So if you see a carbon-carbon double bond, expect it to be nucleophilic. And that's because if you use it as an electrophile, you would generate a C-, and C- are very unstable. Like C+ aren't bad good, but C- are really unstable. You don't make C-. So we make a carbocation. So this carbocation is exactly the one you'd expect to form because it's the more stable carbocation. Like nothing's different here. All the same Markov-Dikov rules. And then we have a nucleophile present. C double bond O is always electrophilic. That's why I record these. Good, I am recording. So we have a nucleophile. Now it could be water, it could be an alcohol, it doesn't freaking matter. We just need something with lone pairs, right? We have a carbocation, it's going to react with basically anything that moves. Why doesn't it react with the acetate? There's an O- here, you're saying, wouldn't that be reactive? Well, it's pretty stable. The other thing is we are drowning in water. There is a ton of water. There's only a little bit of the acetate. This guy is very reactive. So although OAC- might be more reactive than water, it doesn't matter because this guy is so reactive, it's going to react with the first thing that passes by. It's a negative charge. I just suck at drawing. So the water attacks. So the problem here is I can blame a lot of my drawing when I'm drawing on a surface tablet for the low resolution of the surface tablet. This is really, really high resolution, so I can't blame it on that. I have to blame my drawing on this on being a really shitty drawer. Do my best. So we've added water. And then let's get rid of one of those extra protons. I'm just going to use acetate because it's there. You can use water. It doesn't matter. Just the proton needs to go because this needs to become neutral. Okay, so we make that. Now we're not, let me just draw that out, the acetate fully. Now we're not done. Whenever you see one of these questions, it's going to be phrased as something like HGOAC2. And then 2, it's going to say sodium borohydride. Always, 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 always. Madison, doesn't matter. You can use either. I had it drawn out there, so I used the acetate. You could have used water. It would have been, as I said, it was perfectly fine to use water. It doesn't matter which. I just had drawn out acetate. And so it saved me having to draw something else. So I was being lazy. But either one works, as Samantha points out. Okay. This is where the sodium borohydride comes in, because this is actually reasonably stable. I don't love metals making bonds with things, but it's not the end of the world. And so if we have, oh, okay, so there we go. Hopefully it reconnected. Yes, it did. If we had borohydride now, keeping our eye on the mind on the idea that what we're trying to do is do a Markovnikov addition of water. Thinking about that might make sense that we are going to attack the carbon. We are going to break the bond between carbon and mercury. And I'm trying to think if I just want to draw the next arrow. It's the right arrow. Yeah, I'm going to draw it. And we're going to break a carbon-oxygen bond. This is weird. We haven't seen any examples like this where we break a bond to an atom and then an atom breaks another bond. But let's just see what we get coming out of this. So this is that H we just added. We get mercury. And it's mercury metal. Mercury 0. Plus another acetate. And so we've gone from this mercury compound, this mercury 2 compound, mercury acetate, to mercury 0. And we've added in our hydrogen. And so you can really think of this as, like, formally it's a reduction. If you remember your whole Leo the lion says grr thing, we had a mercury 2, it's now mercury 0. We reduced the mercury using the electrons on the hydride. And we actually oxidized the boron because we went from boron losses of electrons. It lost 2 electrons with the hydrogen. So this is called oxymercuration. / demercuration. So you add mercury, you take mercury away. I'm almost afraid to ask. So questions about this? How do you know that H attacks that carbon? So yeah, it's a little weird, right? Because like when we were just talking about the oxygen mercury bond, we were saying, hey, the oxygen's negative, the mercury's positive. And now I'm saying, like, look, I'm attacking a carbon attached to a mercury, and isn't that carbon negative? My cat is agreeing with you. I don't know, do I have my camera on? Yeah, okay. You'll be popular. You're always popular. Zoe is not a very good organic chemist. She's good at pushing arrows off of tables if they're like arrows. Nice. I think you just kind of need to get familiar with the pattern. Yeah. This is the only mercury one you have. So the reason more is that that mercury there is also attached to that other oxygen. And in this case, this mercury oxygen bond is starting to extend. And so the mercury is becoming positive and the oxygen is becoming negative. And so the mercury is becoming positive. It's breaking the carbon-mercury bond, and it's dragging the electrons, trying to drag the electrons towards it, so it makes the carbon positive. So the carbon becomes a good target. I'm right at the edge of the paper, and so it won't let me write there. So the mercury is delta plus here, which makes the carbon next to it susceptible to attack. And a driving force here is the generation of mercury 0 and a release of an acetate, which is entropically favored because you increase the number of molecules present. I don't know if you remember back to first year chemistry, you talked about entropy, and you create more gas molecules, it's always entropically favored. If you create more molecules, it's always entropically favored. So we're going from, you know, the starting material where mercury is making these two bonds to 3 components, mercury and 2 separate acetates. Yeah, so Jeanette, exactly. The idea is to get mercury at the end. It's the driving force. This is the only mercury reaction you will ever need to think about. Mercury is awful. It only gets used like a couple of things in chemistry, and this is one of them. Where the borohydride come down? I just drew the first step, but this is always going to be offered as 1, add mercuric acetate water, 2, add borohydride. If you don't add the sodium borohydride, you stop at this carbon-mercury bond. And you can actually isolate that. Those exist. I wouldn't want to, but you can. Okay. I'm going to try, at the risk of, you know, this being a disaster, but it's a disaster in my lecture. It's just, it's not so much anything about it. It's just really hard. Let's take the same molecule. So we're going to treat this with ozone and dimethyl sulfide. Work through the mechanism. I have it in my lectures. If you look up the mechanism of ozonolysis anywhere, you will find the same mechanism. This mechanism is complicated. It's on the very complicated side of mechanisms, period, all through. Why it's important is because for this class is because the way it's moving functional groups around, the way it turns O bonds into aldehydes, which is what it does, is very, very relevant for this class. But in this case, an aldehyde and a ketone. No, drawing extra bonds for no reason. But the mechanism of itself is kind of beyond the scope of the class, but I'm still going to walk you through it. You know, I'm thinking really hard about this right now, just as I'm drawing this. I'm going, are you responsible for this mechanism? I've always made it for people responsible for this mechanism. How about this year? I commit to saying I am not going to ask you this mechanism on a test, or I'm not going to ask you this mechanism on a test, so it won't be on the final. The reaction will almost certainly be on the final. The mechanism will not be on the final. This is the only mechanism I'm showing you in class that I can guarantee will not be on the final, and that's because I think there's just too many subtleties in here, and it's really easy to mess it up. So what we're doing is we're reacting ozone, which is that does not look like a happy molecule. Notice how many oxygen bonds there are. Yeah, I can ask for the product, and it's going to form parts of sequences, and you might need to know to use this as the reagent to do something, but you don't need to know the mechanism. I still recommend you draw it out a few times, just so that you make sure because you need to know what the product's going to be. And there's no better way to understand that than to know the mechanism. And this is the first reason why you don't need to know the mechanism, because ionically, this is very difficult to make sense of, because I just finished saying that the double bond, carbon-carbon double bond, almost never acts as an electrophile, it always acts as a nucleophile, yet here I have it acting as both an electrophile and a nucleophile in the same step. Julia, that is on your side for your work. That's your job. I can say you're not going to run into any reagents or mechanisms that are not in any of my assignments. Because somebody surprised. Well, there might be versions of a reagent where it's the same thing, like it's a different alcohol. You're responsible for that, but you're not going to run into completely different things that are not in my assignments. So the list is the assignments. So if we do this and we follow all those arrows, we get that. So something that looks better if you make sense of this, right? The negative charge is now, that oxygen is now making a single bond. We now have a single bond between that carbon and oxygen. We've broken the oxygen double bond. This is more stable. Of course it is. This is why ozone reacts. By the way, ozone, really nasty stuff, because it just reacts with freaking everything. But stable is always relative. This is not stable because just look at it. You've got two oxygen single bonds. It's awful. So this falls apart immediately. I have drawn that wrong. So we're using a lone pair on one of the oxygens to form a new oxygen-carbon double bond. We are breaking a carbon-carbon single bond, and we are forming another new carbon-oxygen double bond while breaking another oxygen-oxygen single bond. Wait, what? So just try and follow the arrows. Trust in the arrows. You get that. Now, the right-hand side of that molecule looks perfectly normal. It's an aldehyde. That looks great. The left-hand side of that molecule does not look perfectly normal. It's weird and fucked up. So I'm going to redraw this slightly. I'm going to use my rotating thing. Okay, so what I've done there, if you notice, is I flip my aldehyde around. Now, if we remember how this, talking about resonance structures, reacting from the second most stable resonance structure, for this horrible monstrosity on the top of my molecule, that's the most stable resonance structure. The second most stable resonance structure would have be that. And that's how we're going to react. So we have a carbonyl. We know carbonyls are electrophilic. So we can attack the carbonyl. We need to break the carbon-oxygen bond. That can make a new bond up here. And that's going to force bond breakage there. So we're going to break the carbon-oxygen double bond. Again, it's kind of a carbonyl. It's a carbonyl where the oxygen is positive. So we're using an oxygen to break a carbonyl to break another carbonyl. Now that looks like awful, but when we do it like this, it actually all kind of smooths out a bit. And we get that. So a couple of these have a name. This is called a primary ozonide. This is called a secondary ozonide. The primary ozonide is very, very, very reactive, and it decomposes into the secondary ozonide. So if we think about all of these and we compare the primary versus the secondary, we know what we've done is we've traded an oxygen-oxygen single bond or an additional oxygen-carbon single bond. Like up there on the primary ozonide, we have 2 oxygen-carbon single bonds. In the secondary ozonide, we have 4 oxygen-carbon single bonds and 1 oxygen-oxygen single bond. We've also lost a carbon-carbon single bond. But we've lost one of those really unstable oxygen-oxygen single bonds. That's the whole point. Now nothing more can happen. These exist. You can actually isolate them. We have done it by accident. But generally, if the molecule is not very big, like if I was trying to isolate the thing I'm looking at here, I would blow up because it wants to become oxygen gas, and that's going to be very exothermic, and it will explode. So normally you never isolate these. I'm going to flip the page. And I'm going to flip back because I almost lost track of what the hell I was drawing. It's a 6-membered ring. That's what we had. This is when that second reagent comes in now. Because this is stable, this can't do anything more. And this is just cut. So going back and harkening back to the idea, we have that iodine-iodine bond. And at any one time, one of those iodines was positive and the other one was negative. You have the same effect if you have an oxygen-oxygen single bond. So it doesn't matter which of these I do this to. I'm going to attack one of those oxygens, and I'm going to release an O-. Why am I attacking an oxygen when there are carbons around which are more electrophilic? Because if I attack an oxygen, I can break the really, really weak oxygen-oxygen single bond. If I attack a carbon, I have to break a carbon-oxygen single bond, which is pretty strong. I get to break the weakest bond because I can do this. Thank you a lot, Faith. I really appreciate that. Hey, Samra, that's whatever I said. I think Faith gets 0.2% because she caught an error in my thing. So if you can note that, if you're here. Samra's not here. Okay, good job, Faith. Noting it to the side here. Okay. So we attack one of the oxygens. And if we do that, let's draw that 6-membered ring. Just going to draw this intermediate. It's a valid Lewis structure, but it doesn't exist for any length of time. We'll see why. We'll have that, right? The sulfur is positive now because it's making lost some electrons. The oxygen we just released is negative. And now this thing can unfold into something natural. No, there's no positive on any of the oxygens. The oxygen's neutral. So the sulfur has attacked the oxygen, so the sulfur became positive, and this oxygen becomes negative. So there's no positive charge on any of the oxygens here. And now what can happen is this O- makes a new oxygen carbon double bond. This is kind of acetal chemistry, right? That's just an acetal. That's a hemiacetal there. And on the other side, that's the difference between the tablet. If I draw a line like that on my tablet, I can erase the whole thing by pressing it once. With this, I have to everything. That's irritating. So you have an acetal here, and you have an acetal here. And so we're going to break both those acetals. And we generate our two aldehydes. And this thing, which is in resonance with something that doesn't have any charges. This is called Dmso. It's a major, really, really important solvent. Actually, almost all drugs are dissolved in it because it dissolves absolutely everything. And it's safe. So it's one of the very, very few organic solvents that I can inject into your veins and you won't die instantly. So it's kind of nice. But, you know, making DMSO is not the point of this. The point of this is to make the dialdehyde. So overall, what we've done is what we sketched at the beginning here. We went from a double bond. We used scissors, molecular scissors, to cut the double bond in two, and we stuck oxygens on both sides. So we really oxidized the crap out of that molecule. We basically went from a carbon-carbon double bond to two carbon-oxygen double bonds. And the oxygens came from the ozone. And the third oxygen, ozone, went on to DMSO. Hard mechanism, completely agree. Work through it. I think it's a good reason to work through on your own a few times. And I think I draw some easier examples that aren't rings, so you don't have this stupid ring thing going on. Is that it talks a lot about a lot of the fundamental things we've been discussing about where charges want to be and how charges want to react. Okay. So I want to talk, if there's no specific questions, I want to talk about today's subject a little bit, just do a problem or two. So what we've been doing so far is we've been adding yeah, absolutely, Olivia, that's the whole point. There's a hydrogen attached right at the end. Well, no, there's a hydrogen that's on here that's just, it's present. I didn't have to draw it. It's assumed. So I think that's the one we're talking about, Madison. It was there the entire time. It's just we didn't draw it in because it just crowded everything. Yeah, okay, good. Yeah, go ahead, Olivia. Let's do that. Okay. So while that's coming up, I'm just going to finish a few more notes here. So what we've been talking about so far is adding electrophiles, then nucleophile. You know, assuming it's Markovnikov, we get that. And this goes through a carbocation. Yeah, I'm sorry. I think I must have erased something. Yeah, thanks, Melissa. I think when I was erasing my circle, I erased that arrow. Thank you. Yes, absolutely. And that bond is coming from that bond to that bond. We're kind of you can draw an intermediate where you get an O minus if you like, or you can just immediately draw the carbonyl. The lone pair in there is confusing matters a bit. Okay. So I'm going to expand what Olivia is showing me. Okay. How you got from the first molecule to the second molecule. So I don't know if you guys can see this. There we go. I don't know if you see what I see, or if I'm eliminate, or if you don't, because it's the MS Teams thing itself. But if not, you can take a look at what Melitza put up there. And you'll see that what we have is we randomly have an iodine leaving. Okay. So what she's drawn is so at the top there is what we've been doing, which is, you have a carbocation, you react it with a nucleophile, and it becomes the product. And we got the carbocation by activating a double bond with H+. Here what we're doing is we're thermally breaking a weak carbon bond. So a carbon iodine bond is a weak bond because halides bonds are all kind of weak. Now, this is called the SN1 reaction because what's happening is, think of every bond as basically two balls held together at the end of a spring, and they're vibrating. Bonds are always vibrating. And the stronger the vibration, the more they can shake, right? And if the spring's not very strong, they can snap apart and the spring can break and the two molecules go flying off in different directions. Now that becomes a lot more likely when you make the springs vibrate faster, right? Because then you're going to get more motion. Just think of any spring that you can imagine, or like even a swing. And the way you make things vibrate faster is you add heat. So carbon halide bonds, carbon halide bonds are weak-ish, like the springs are vibrating. And so you put enough heat in and eventually it will snap open. Now, if there's enough iodine, if there was tons of I- present, there's nothing stopping the iodine coming right back and going straight back to starting material. Nothing stopping that if there's tons of I- present. But you're insolvent. You have a lot of ethanol present. So there's a little bit of iodine, and occasionally it shakes itself loose, forms a positive charge. Maybe a lot of the time the iodine comes right back in, regenerates the starting material, but occasionally you've got some ethanol that comes in. And that makes product. Well, it makes that, which then loses. Again, just to answer somebody's question that's going to come, yes, you can equally use I- to take off that H, that's fine. The ethanol is more likely, to be honest, but I would take the marks off. That way it doesn't look like an arrow, does it? And now we made a carbon-oxygen bond. And that carbon-oxygen bond is a much stronger spring than a carbon-iodine bond. So if you heat this long enough, even if the iodine does come back in and regenerate the starting material, eventually you're going to break all the carbon iodine springs and replace them with much, much stronger carbon oxygen springs. So Madison asked, for SN1 and SN2, I'm confused as to how to know when something is an intermediate or not. Something is an intermediate if it is a valid Lewis structure. If you draw it when you're drawing your reaction mechanism and it's a valid Lewis structure, it's an intermediate. So this is what I've drawn there, that carbocation. This is an intermediate. There is nothing wrong with it as a valid Lewis structure. It is a perfectly fine Lewis structure. This guy is also an intermediate. Anything that isn't your starting material or product and is a valid Lewis structure is an intermediate. Your starting material is not an intermediate, it's your starting material. It's where you started. And your product is not an intermediate, it's your product. It's where you end up. An intermediate is between your starting material and product. A transition state is any non-valid Lewis structure that leads from one to the other. So the transition state for the SN1 . So again, your transition state is generally your energy maximum, your local maximum. So if you go back to your calculus, you guys have all done calculus, right? I know you have to like get into this program or any of these programs. I'm not going to ask you to derivatize anything, I promise. But just if we're thinking about curves, so normal. Sorry, I'm thinking of an SN2. So these are your transition states. They're your local maxima. They're the point at which you put as much energy as you can into breaking bonds, because breaking bonds take energy, but you haven't yet gotten the benefit of making the bonds. So what does the transition state of an SN1 look like? The most important one is the one of the rate determining step. Again, to figure out which one's the rate determining step, you compare the activation energies. The one that's bigger is the one that's rate determining. RDS. So if we're thinking about it, what does that look like? So that's our starting material, the transition state, and notice I'm going to put this in brackets because it is not a valid Lewis structure. Why is it not valid? Well, you can't have dotted lines in a Lewis structure. And what I've done there is I've sort of shown that the bond is extending. It's getting longer. I'm just going to draw this shadow of a wedge in behind it because it's coming out towards us, but it's getting longer. Those dots don't mean it's going back and away from us. It just means the bond is a partial bond. So we're breaking that bond, and as the bond is breaking, the carbon is getting positive, the iodine is getting negative, and we put in the maximum amount of energy. But we haven't completely broken the bond. So then the question is, wait a second, wouldn't it take more energy to completely break the bond than to only partially break the bond? Yes, but. And the but is this iodine is still close to this carbon chain. It doesn't have freedom of movement. You haven't yet gotten an entropic benefit from breaking the carbon iodine bond. Things aren't shaking loose and able to go their separate ways, and entropy being able to take over. And I've got a cattail making a cameo. So lectures are better with cats, right? That's why we're like catalyzing so much in chemistry. The bond is getting longer and longer and longer, but things haven't drifted away to infinity. So you've had to put all this energy in to break the bond, lengthen it out, lengthen it out, lengthen it out, but they're still tied together, so they can't shake loose, so you don't get this big entropic benefit. A little bit more energy, boom, the iodine's gone, and now it's flying around like crazy, and the carbon's flying around like crazy, and everything is happy entropically, although the carbon's really, really unhappy because it is now moving to the intermediate, which is a valid Lewis structure, and it is a carbocation. But it's slightly more stable than that because what we haven't drawn in there is there's an I- floating around as well somewhere else. It forms part of that total energy system of that intermediate, and it's pretty stable. And it's like entropically just able to go anywhere it wants. So transition states must always be in brackets. They don't really exist. So they're not discrete species. You can't isolate a transition state ever. You can never see a transition state. It's a place you have to pass through, but the molecule spends 0 time at the transition state. It's the highest possible energy point. So you're going to go forward or backward from that point. You have no choice. You're not staying where you are. And they're never valid Lewis structures. Because you always have partial bond formation, partial bond breaking in a transition state. If you aren't partially forming or partially breaking a bond, it's not a transition state. Because chemistry involves bond making and bond breaking. So if you're not making or breaking a bond, you're not doing chemistry. I guess any follow-up questions to that, Olivia, or? I guess not. 2:20. Those of you who have a lab, enjoy. Those of you who don't have a lab, enjoy your weekend. And those of you who have a lab in some other course, I feel really sorry for you. So have a good rest of your day, and I will catch you all up. And I'm glad it makes perfect sense. I know you're being nice, but still, hopefully it helps. I'll be posting this soon. The assignment is till Monday night. Yeah, I want to make sure that you have a day of week, right? Just for anyone who, I know we have some people who can't work on Sundays. We have other people who cannot work on Saturdays. So I'll make sure that there's some time during a weekday. Yeah, Madison. Oh, you had your hand up, but then you put your hand down. Now you have your hand up.
Yes, but it's not regarding course content. It's
Okay.
regarding a lab question about chair conformations.
Okay.
Okay. Just let me pull it up real quick.
I might be able to answer. I might have to decline to answer.
Okay, no worries. I already took the lab yesterday, but I was just contemplating on like the theory behind it.
Okay. That's fair. I'm always happy to talk about that. So if you want to pull it up and share your screen.
Dr. Trant, can I just ask a quick question about the assignment?
Yes.
Is it covering only, like, I know you said up to last Friday, but does it cover the things like that were after the previous assignment, or is it just simply after the midterm? Like, will it have
after the previous assignment? Yeah.
Okay, so it'll have like enantiomer chirality.
Yes, it'll have like assign RNS to things.
Okay.
Starting there, because I think, yeah.
Okay. All right. Thank you.
And then it's going to end with carbonyl stuff.
Okay.
Yeah. Jeanette, there is no information on the midterm marks. No, I do want to hear that because I feel really guilty about this, and we're trying to get all the GAs together to do this. So we're hoping to get it done this weekend or early next week. You're getting your marks by the end of next week. It's been ridiculous. And this has been insane. I'm sorry for this. Yeah. Yeah, I don't care what anyone else has on their schedule. It's been long enough. You guys are getting your marks by the end of next week. Hopefully early next week. And if anyone's really delaying, I'll just mark them all myself, and that's fine. I just don't want to do that. It's just a lot of questions. There's 340 of you. Okay, Madison, do you have your screen?
Okay, yeah. Can you see it?
Yeah.
Okay. So I didn't want to show the one that I filled out just in case
Yeah,
there was
no,
a wrong
it's good.
answer.
I think anyone who's going to do the lab is probably left for the lab now, but
Yeah. Is this the right one? Yeah. Okay. So it's question 9.
yeah.
It was talking about trichloral. You can read it. And I don't want to pronounce that word. So it's basically between the chlorine atom and then the fluorine atom. And it was saying that the chlorine one is smaller, but then I thought, why would that one be smaller when it has a larger atomic radii? And it takes up more space than the fluorine. But I guess it's mainly because of the electronegativity and how fluorine is more electronegative than chlorine. But that doesn't really, I don't really understand how electronegativity affects like steric strain and stuff like that.
Okay.
And the chair conference.
Okay, let's work through this. So I'm gonna give it. You know what? It's a really good question. Can I send you the answer over email?
Yes.
Just I want to make sure because it's a good theoretical question. I actually really proud they came up with this one. I haven't seen the lab questions, but it's worth explaining over email just because I know that there's still an actual lab happening today.
Yeah.
Okay.
Because I just didn't remember talking about electronegativity and its contribution to steric strain in the lectures. So I was just like, don't know.
Yeah. Because we didn't discuss that because it's something a bit more. This requires a little bit of thinking. So I will send you this tomorrow morning just because the lab will be over by then.
Yeah, that makes sense.
In the meantime, you're on the right track with how you're thinking. If you have the mental energy for this, think through what the ramifications are of having the more electronegative atoms on there.
I think I may have an idea, but if
okay. I'll send it to you by email. Okay.
Okay.
Cool. Good. Tricky question. Okay. Take care.
Great. Thank you. Have a great
Bye,
day.
everybody. Have a good day.